Imagine a planet almost the same size as Earth, wrapped in brilliant clouds, but turning the wrong way. On Venus, the sun would rise in the west and set in the east, if the clouds ever allowed it to be seen. Its day lasts longer than its year, and scientists still trace the cause through ancient impacts, solar tides, and a crushing atmosphere that may tug on the planet itself. This is the strange reason Venus spins backwards. If this quiet journey into space brings value, please like the video, subscribe to the channel, and continue into the hidden motion of Venus. From a distant view of the solar system, Venus rests as the second planet from the Sun, moving inside the orbit of Earth and outside the orbit of Mercury. It belongs to the inner group of rocky planets, where worlds are made mostly of stone and metal rather than deep layers of hydrogen and helium. In this wide setting, Venus appears at first to be a familiar kind of planet. It is close in size to Earth, close in mass, and close enough in distance that it often becomes the brightest planet in Earth's sky. Yet its motion carries one of the quietest and strangest differences in the solar system. Venus turns in the opposite direction from most planets, and it turns so slowly that its rotation becomes less like a daily rhythm and more like a long planetary drift. Most planets in the solar system rotate in the same general direction in which they travel around the Sun. This shared pattern reflects the ancient motion of the cloud of gas and dust from which the Sun and planets form. The cloud turns as it collapses, and its turning motion is partly preserved in the orbits and spins of the bodies that grow inside it. Earth follows this common direction. Mars follows it as well. Jupiter and Saturn also spin in this broad family pattern. Though much faster than the rocky planets, Venus does not follow it. Its spin is retrograde, which means that the surface turns opposite the usual direction. This fact is simple to state, but it opens a deeper problem. A planet is not expected to reverse easily. A whole world carries great rotational momentum, the stored motion of a spinning body. Changing that motion requires force, time, or both. At this outer scale, Venus is seen not as a single mystery but as part of a system shaped by formation, gravity, sunlight, atmosphere, and time. The Sun sits at the center as the main source of gravity and heat. Around it, the planets keep their paths through a balance between forward motion and inward pull. Venus moves along its orbit in the same direction as Earth and the other major planets. Its orbit is not backward. Its revolution around the Sun belongs to the common order of the solar system. The unusual part lies in the way the planet turns around its own axis. This separation matters. A planet can travel one way around the Sun while spinning another way on its axis. Orbit and rotation are related by origin, but they can be changed by different processes. From far away, the axis of a planet can be imagined as an invisible line running through its center, from one pole to the other. Rotation is the planet's turning around that line. On Earth, this turning produces the familiar cycle of day and night. On Venus, the same idea applies, but the rhythm is profoundly different. Venus takes about 243 Earth days to complete one rotation relative to the distant stars. This is longer than its year. Because Venus takes about 225 Earth days to complete one orbit around the Sun, the slow backward turn creates an unusual relation between day and year. The Sun would not appear to move across the Venusian sky in the same way it does on Earth, though the dense cloud cover prevents any ordinary view from the surface. The distant view also shows why Venus invites comparison with Earth. The two planets are often described as similar in size and mass, but this comparison can mislead when it suggests similar histories. Earth rotates once in about 24 hours. Venus rotates once in a period longer than an Earth season. Earth has oceans at the surface and a thin atmosphere by planetary standards, Venus has a massive atmosphere dominated by carbon dioxide and wrapped in thick clouds of sulfuric acid. Earth's rotation helps shape winds, ocean currents, weather systems, and the magnetic field environment around the planet. Venus's slow retrograde spin belongs to a different balance of forces, where the atmosphere and the sun's pull become especially important. Even from this wide view, brightness becomes part of the story. Venus shines strongly because its cloud cover reflects a large fraction of sunlight. This bright outer appearance hides the surface completely from ordinary visible light. For centuries, the planet's true rotation remains difficult to know because no solid landmarks can be followed through the clouds. A planet can seem calm and steady while concealing a motion that runs against expectation. The backward spin is therefore not only a mechanical feature, it is also a hidden feature, discovered only when instruments begin to pass beyond brightness and measure the world beneath it. The solar system provides other reminders that planetary rotation is not perfectly uniform in origin or outcome. Uranus is tilted so strongly that it rotates almost on its side. Mercury turns slowly in a pattern shaped by the sun's tidal influence. The large planets spin quickly, while the smaller rocky planets vary more. These differences show that early formation gives planets a starting motion, but later history can reshape it. Impacts, tides, internal friction, and atmospheric effects can all matter. Venus stands among these examples as a case where the final spin is not only slow, but reversed. The reason is not settled as a single simple cause. Observations indicate the present state clearly, while the path that produced it remains a subject of scientific explanation with more than one contributing process. At the outermost level, the strange spin of Venus is therefore framed by contrast. The planet moves normally around the Sun, but it turns abnormally on its axis. It resembles Earth in size, but not in atmosphere, surface environment, or rotational rhythm. It shines brightly, but hides the very features needed to read its motion. It belongs to a system born from a rotating disk, yet its own rotation does not preserve the common direction. This contrast is the quiet doorway into the subject. The reason Venus spins backward cannot be found by looking only at its present surface or only at its orbit. It rests in the long interaction between the planet and the environment around it, beginning with the broad architecture of the solar system and narrowing gradually toward the forces that act on Venus itself. Venus follows a path around the Sun that is almost circular compared with the paths of many other planets. Its orbit is only slightly stretched, so its distance from the Sun changes less than the distance of Earth changes during a year. This nearly even path gives the planet a steady setting for heat and gravity. The Sun remains close, large, and dominant in its sky, even though the thick cloud cover prevents the surface from seeing it directly. From the outer region of the planet's motion, before the atmosphere and surface are considered, Venus is first a body moving through sunlight, held in a smooth track by the Sun's gravity. The orbit of Venus lies inside the orbit of Earth. Because of this position, Venus never appears far from the Sun in Earth's sky. It is seen near morning or evening, depending on where it stands along its path. This visible behavior has been known since ancient times, but the orbital meaning becomes clearer when the solar system is understood as a set of planets moving around a central star. Venus is not wandering freely. It is bound to the Sun, falling inward constantly while also moving sideways fast enough to keep missing the Sun. This balance produces its year, a complete circuit that lasts about 225 Earth days. The orbit matters because a planet's spin cannot be separated fully from the gravity field in which it moves. Rotation is the turning of the planet around its own axis, while revolution is the motion of the planet around the Sun. These two motions are distinct, yet gravity can connect them over long spans of time. The Sun raises tides on planets, not only in oceans when oceans exist, but also in solid rock and atmosphere. A tide is a slight stretching caused by the difference in gravitational pull across a body. The side nearer the Sun feels a little stronger pull than the side farther away. This difference is small compared with the whole pull of the Sun, but over long periods it can influence the turning of a planet. For Venus, the closeness of its orbit makes solar tides more important than they would be for a similar planet farther away. The Sun's pull is stronger at Venus than it is at Earth. The sunlight is also stronger. These two facts create the outer conditions for the planet's later behavior. The stronger gravity provides a repeated tug on the solid body. The stronger sunlight heats the atmosphere and gives it motion. At this stage of the path, the details remain outside the frame. But the orbit sets the strength of the influences that act on Venus. A planet nearer the Sun does not simply receive more light. It also lives deeper inside the Sun's gravitational reach. The nearly circular nature of the orbit gives Venus a steady pattern of solar forcing. Solar forcing means the energy and influence delivered by sunlight and solar gravity. On a more stretched orbit, a planet moves much closer to and farther from the Sun during its year, and the changing distance can make seasonal or tidal effect vary more strongly. Venus has little such variation. Its orbit keeps the planet under a fairly constant level of solar heating. This steadiness does not make the planet calm at the surface, but it gives the outer frame a simple shape. The planet moves through a persistent bath of light and gravity, without large swings in distance. The orbital plane of Venus is also close to the plane in which Earth orbits. This shared flatness reflects the ancient disk from which the planets formed. The early solar system is not a scattered cloud by the time the planets grow. It becomes a broad rotating disk, with most solid material moving in related paths around the young Sun. Venus still carries this ordered motion in its orbit. It travels around the Sun in the same prograde direction as the other major planets. Prograde means moving or spinning in the main direction shared by the solar system. In its path around the Sun, Venus is prograde. The backward part of its motion is not found in the orbit, but in the rotation of the solid planet. This distinction gives the first important boundary around the mystery. The planet has not been turned into a backward traveller around the Sun. Its orbital motion remains ordinary. The strange feature is more local, tied to the planet's own axis. From the scale of the orbit, Venus appears obedient to the broad history of the solar system. Its year, its direction around the Sun, and its placement among the inner planets all fit the common pattern. The rotation alone departs from it. This makes the problem narrower and more precise. The cause must explain why the spin changes while the orbit remains regular. The slow orbital year also shapes the way the backward rotation is measured. Because Venus takes about 225 Earth days to go around the Sun, and about 243 Earth days to rotate relative to the stars, the relationship between its year and spin is unusual. The rotation period is longer than the orbital period. A day measured by the Sun would not match the sidereal rotation period, because the planet is also moving around the Sun while it turns. Sidereal means measured relative to the distant stars. This distinction is useful because a planet's spin can be measured against the distant sky even when sunlight creates a different surface day. Venus shows how orbit and rotation combine into a pattern unlike the one familiar on Earth. From the orbital region, no single cause appears by itself. The orbit does not announce why Venus rotates backward, it only defines the environment in which the explanation must work. The planet is close enough to the Sun for tides to matter. It receives enough sunlight to drive a massive atmosphere. It has a nearly circular path that keeps these influences steady. It travels in the ordinary direction around the Sun, showing that its backward spin is not a reversal of its whole motion. These outer facts form the frame of the subject. Before any hidden surface is reached, before any radar measurement is considered, Venus is already placed in a quiet but powerful setting, moving along a smooth, bright path where the Sun's gravity and light provide the first conditions for its strange, slow turn. From Earth's side of space, Venus first presents itself through light. It is not seen as a dark, rocky globe, but as a brilliant point, brighter than any star in the night sky. This brightness comes from the planet's thick cloud cover, which reflects much of the sunlight that reaches it. The measure of reflected light is called albedo, a term for how much incoming light a surface or atmosphere sends back into space. Venus has a high albedo because its clouds form a nearly complete pale cover around the planet. The solid surface is hidden beneath this bright shell, and the hidden surface keeps the true motion of the planet out of ordinary sight. The brightness of Venus creates a simple but important difficulty. A rotating world can usually reveal its spin through visible markings. Mars shows dark and light surface regions that move with the planet. Jupiter shows bands and storms that trace motion in its atmosphere. Earth shows continents, oceans, clouds, and ice. Venus, by contrast, shows a smooth cloud face in visible light. The cloud patterns change, but they do not provide a clear view of the ground. The planet's surface does not appear as a set of stable marks that can be followed from one night to another. The first visible region of Venus is therefore not the rotating stone world itself, but the sunlight reflected by clouds above it. This outer brightness has shaped the human understanding of Venus for a long time. Before instruments can penetrate the cloud cover, the planet's size and orbit can be measured more easily than its spin. Its phases show that it circles the Sun inside Earth's orbit. Its changing apparent size shows that its distance from Earth varies as the two planets move. Its brightness shows the power of reflection from its atmosphere. Yet none of these visible traits reveals the direction of the solid planet's rotation. The planet is close and bright, but its most basic daily motion remains concealed. In this way, Venus becomes a reminder that brightness is not the same as clarity. The clouds reflect sunlight because they are made mainly of droplets that include sulfuric acid. Sulfuric acid is a compound formed from sulfur, hydrogen, and oxygen. And in Venus's atmosphere it exists as tiny droplets suspended high above the surface. These droplets scatter light efficiently, spreading sunlight in many directions and sending a large part of it back into space. The cloud layer is not a thin veil. It is a deep and continuous system, covering nearly the entire planet. In visible light, this system acts like a screen. It shows the presence of the atmosphere while hiding the land below. From the outer level of observation, the whiteness and brightness of Venus can seem calm. The planet has no visible continents, no blue oceans, and no exposed polar caps. It shines with a steady beauty that gives little hint of its slow backward rotation. The reflective cover smooths the planet's appearance. Even when telescopes improve, the visible surface remains inaccessible. Subtle markings appear in ultraviolet light, where some cloud features absorb more sunlight than others. But these markings belong to the atmosphere rather than the ground. They reveal motion in the cloud layer, not the exact turning of the solid globe beneath it. The distinction between atmospheric motion and planetary rotation is essential. A cloud can move faster or slower than the surface below. It can move in a different pattern because winds are driven by heat. pressure, and the rotation of the planet. On Venus, the upper clouds move around the planet much faster than the solid body rotates. From the level of brightness alone, this creates a misleading impression. Features in the clouds can circle the planet in only a few Earth days, while the ground takes about 243 Earth days to complete one turn relative to the stars. The bright outer face is active and flowing, but it does not directly show the movement of the solid planet. The light from Venus also carries information about the planet's energy balance. Sunlight arrives from the sun. Some of it is reflected by the clouds, and some is absorbed by the atmosphere and surface. The reflected portion makes Venus bright from afar. The absorbed portion helps maintain its extreme heat at this outer visible level. The important fact is that the clouds control what leaves the planet as reflected light and what remains hidden beneath. The same cloud cover that makes Venus easy to notice also makes it difficult to interpret. The planet can dominate the evening sky while keeping its rotation unknown to simple observation. Scientific understanding changes when observation moves beyond ordinary visible light. Radar becomes especially important because radio waves can pass through the clouds and bounce from the solid surface. Radar is a method that sends radio waves toward an object and measures the returning signal. It does not depend on sunlight reflected by visible clouds. In the story of Venus's spin, radar eventually provides the means to look through the bright cover and measure the surface. Yet within the region of light and brightness itself, the main role of the clouds is concealment. They define the outer mask of the planet. This mask also affects how the planet is imagined. A bright world in the inner solar system might once suggest warmth, closeness, and Earth-like conditions. The visible face gives no direct sign of crushing pressure, volcanic plains, or backward rotation. The eye receives reflected sunlight, not the deeper truth of the surface. The physical reason is straightforward. Visible light cannot pass through the thick global cloud system and return with a clear image of the ground. The information is blocked, scattered, and replaced by the shining upper atmosphere. Venus becomes a world whose outer appearance is almost entirely atmospheric. The strange backward spin therefore begins, from the observer's perspective, as a hidden fact behind reflected light. The planet's orbit is known, its brightness is obvious, and its position near the sun is plain. But the rotation of the rocky body cannot be read from the glow. The bright cloud shell stands between the distant observer and the turning planet. It creates the first visible boundary on the inward path, a luminous layer that is not still, not solid, and not transparent. In this region, Venus is a shining object whose beauty comes from concealment and whose most unusual motion waits beneath a cover of light. Above the hidden surface of Venus, the upper cloud decks form a moving shell that belongs to the atmosphere rather than to the ground. This region lies high in the planet's air, where sunlight reaches the cloud tops and where the planet shows its bright face to space. The clouds do not simply sit above the planet as a still covering. They flow around it. Their motion is fast compared with the slow turning of the solid globe beneath them. In this upper region, Venus reveals a striking separation between the spin of the planet and the movement of its atmosphere. The upper clouds are located roughly tens of kilometers above the surface, in a level where pressure and temperature are far less extreme than near the ground, though still unlike Earth in chemistry and structure. These clouds are made largely of sulfuric acid droplets mixed with gases from the carbon dioxide atmosphere. They form layers and hazes that stretch around almost the entire planet. In visible light, they create the smooth bright disk seen from afar, in ultraviolet light. They show patterns of darker and lighter regions, caused by substances that absorb ultraviolet radiation. These patterns allow scientists to track winds high above the surface, even though the surface itself remains hidden. The motion of these cloud features shows that the upper atmosphere circles Venus in only a few Earth days. This is much faster than the solid planet rotates. The term often used for this behavior is superrotation, which means that the atmosphere moves around the planet more rapidly than the planet itself turns. On Venus, superrotation is not a small effect. It is one of the main features of the upper atmosphere. Winds at cloud-top levels can move at hundreds of kilometers per hour, carrying the clouds around the planet while the rocky body below turns with extreme slowness in the opposite direction from most planets. This fast atmospheric motion does not mean that the entire planet spins quickly. It means that the upper air has its own circulation, driven by sunlight, pressure differences, waves, and the exchange of momentum within the atmosphere. Momentum is the quantity of motion carried by matter. In an atmosphere, moving air can carry momentum from one region to another. Waves can also transport it, even when the air itself does not travel all the way from one place to another. These processes are complex, but the basic result is clear. The upper cloud region of Venus is not tied tightly to the slow surface. It races around the planet in a broad, persistent flow. The direction of the upper cloud motion is connected to the planet's retrograde rotation, but the atmosphere does not behave as a simple painted mark on a turning ball. If the clouds were fixed to the surface, their movement would show the rotation of the solid globe. Instead, they slip and flow above it. The cloud tops complete circuits far more rapidly than the land below. This makes the upper atmosphere an active layer in its own right. It is not merely a cover. It is a dynamic system that stores and moves energy and momentum around the planet. Sunlight is a major source of energy for this region. Venus receives stronger sunlight than Earth because it orbits closer to the Sun. Much of that sunlight is reflected, but some is absorbed in and near the cloud layers. The day side of the atmosphere is heated differently from the night side. This difference helps drive winds and waves. Because the planet rotates so slowly, the pattern of solar heating changes slowly relative to the ground. But the atmosphere responds through circulation that can be much faster than the solid rotation. The upper clouds therefore carry the imprint of both strong sunlight and slow planetary turning. The cloud-top winds also show why visible observation can mislead. A marking in the upper cloud layer may move around Venus quickly, giving an impression of rapid circulation, but that motion belongs to air and cloud particles, not to the underlying rock. The solid planet turns backward at a much slower rate. This distinction becomes important in understanding the strange spin because the atmosphere itself may take part in long-term exchanges of motion with the solid planet at the upper level. However, the focus remains on the moving shell seen from space, where the clouds race across a hidden world. The upper clouds are arranged in broad bands and patterns, though they're not as sharply striped as the clouds of Jupiter. Venus lacks the strong day-night surface contrast that would exist on an airless slow rotator because the thick atmosphere redistributes heat. At the cloud tops, waves and changing patterns appear, including large-scale structures that can stretch across wide regions. These patterns show that the atmosphere has layers of motion, not a single simple wind. The cloud deck can contain turbulence, wave trains, and broad circulation cells. Each feature belongs to the outer air, not to the land beneath it. The height of this region also matters. Far above the surface, the air is thinner than below, so it can move quickly under pressure differences and wave forces. The planet's slow rotation weakens some effects that dominate Earth's weather, such as the strong deflection of winds by rapid rotation. This deflection is called the Coriolis effect, a change in the apparent path of moving air on a rotating planet. On Venus, the slow solid rotation changes how this effect works. The atmosphere still circulates, but it does so under a different balance of forces than Earth's atmosphere. The result is a global flow that is unusual in both speed and persistence. The upper cloud decks also connect the planet to space through radiation. They reflect sunlight outward and emit heat upward from the atmosphere below. They absorb some wavelengths and allow others to escape. In this way, they help set the visible and thermal appearance of Venus. Yet they do not reveal the surface. They are both an energy boundary and an observational boundary. Their fast motion can be studied from orbit and from Earth-based telescopes, but their movement must be separated carefully from the rotation of the planet itself. In the inward path toward understanding Venus's backward spin, the upper cloud decks form the first moving layer. They show that the atmosphere is not passive. They show that the visible face of Venus moves at a pace very different from the ground. They show that sunlight can drive fast circulation above a planet whose solid body turns with great slowness. This region does not by itself explain why Venus spins backward, but it establishes a necessary fact. The atmosphere has motion strong enough to matter, and the bright clouds that hide the surface are also part of the physical system that shapes how the planet exchanges energy and momentum over time. Below the upper cloud decks, Venus's middle atmosphere becomes a deeper and heavier region, still far above the ground, yet already removed from the simple brightness seen from space. This layer contains much of the cloud system and the surrounding haze, with carbon dioxide as the dominant gas and sulfuric acid droplets suspended through broad levels of air. It is not a clear sky in the Earth-like sense. It is a thick planetary envelope, dense enough to hold heat, transport momentum, and connect the upper winds to lower regions. In this middle atmosphere, the strange rotation of Venus is approached through the weight and movement of air. The middle atmosphere is not a rigid shell. It changes with height, temperature, and sunlight. Gases move upward and downward. Winds shift around the planet and waves travel through the air. A wave in an atmosphere is a moving disturbance in pressure, temperature, or wind. It can carry energy and momentum even when the air itself only oscillates locally. On Venus, such waves matter because the atmosphere is massive. A small effect repeated through a dense global layer can become important over long periods. The middle atmosphere therefore acts as a broad zone of transmission between sunlight above and the heavier air below. Carbon dioxide gives this region its main character. It is a gas made of carbon and oxygen, and on Venus it forms most of the atmosphere. Carbon dioxide absorbs infrared radiation, which is heat radiation emitted by warm surfaces and air. This absorption helps trap heat within the lower atmosphere and surface environment. In the middle layers, carbon dioxide also participates in the vertical structure of temperature and pressure. The atmosphere becomes thinner with height, but even at high levels it remains part of a connected system. The gas does not merely surround the planet, it influences how energy is stored, moved, and released. The cloud material in this region adds another layer of complexity. Sulfuric acid droplets form where sulfur compounds and water vapor interact under sunlight. The droplets scatter and absorb radiation, helping shape the planet's bright appearance and thermal balance. They are tiny, but they are spread across enormous volumes. Their presence changes how sunlight penetrates downward and how heat escapes upward. The middle atmosphere is therefore not just a place of gas motion. It is also a place where chemistry and radiation help determine the strength and location of heating. Heating differences create pressure differences, and pressure differences drive winds. The winds of the middle atmosphere remain linked to the super-rotating flow above. They are part of the same broad circulation, though speed and direction can vary with altitude. The atmosphere of Venus moves as a layered system, with faster flow near the cloud tops and different patterns below. Because the solid planet rotates so slowly, the atmosphere cannot be understood by simply applying Earth's weather patterns. Earth's daily rotation strongly organizes winds into familiar belts, storms, and moving pressure systems. Venus rotates with such slowness that sunlight and atmospheric thickness take on a different role. The air has time to respond to broad heating patterns, and the deep atmosphere smooths differences that might otherwise be sharp. In this middle region, the idea of atmospheric torque becomes important in a plain way. Torque means a twisting influence that can change rotation. When mass moves around a planet, and when pressure is distributed unevenly, the atmosphere can exert tiny twisting effects on the solid body. These effects are not sudden. They're not like a single collision. They're gradual exchanges between air and rock, carried through friction, pressure, and gravity. On Venus, the mass of the atmosphere is large enough that such exchanges cannot be ignored. The middle atmosphere is part of the reservoir of moving material that may help explain how the planet's spin reaches its present state. Solar heating creates atmospheric tides in Venus's air. An atmospheric tide is a regular shifting of air caused by heating from the sun, somewhat like an ocean tide but driven strongly by temperature as well as gravity. When sunlight warms one region more than another, the air expands, pressure patterns change, and mass shifts around the planet. On a world with a thick atmosphere and slow rotation, these thermal tides can become especially significant. The middle atmosphere is a major part of the region where these tides form and travel. Their movement can transfer angular momentum, the measure of rotational motion, between the atmosphere and the solid planet. This does not mean that the middle atmosphere alone reverses Venus. The present scientific view does not reduce the backward spin to one simple layer. Instead, this region shows how the atmosphere becomes a participant in the planet's rotational history. The air has mass. The mass moves. Its movement is shaped by sunlight and gravity. Over long spans, the atmosphere can influence the rotation of the body beneath it. In most familiar experience, air seems light and unable to affect stone. On the scale of a planet, the meaning changes. Venus's atmosphere is so massive that its motions become part of the mechanical story of the whole world. The pressure in the middle atmosphere increases downward. Each lower level carries the weight of all the air above it. This gradual increase gives the atmosphere a layered heaviness, a sense of growing inward force. High above, the cloud tops move quickly and reflect sunlight. Deeper down, the air becomes more compressed, warmer, and more tightly bound to the planet. The middle atmosphere stands between these two conditions. It is not yet the crushing lower air, but it's already part of the deep pressure system that makes Venus so different from Earth. It marks the transition from the visible cloud shell into the massive body of air surrounding the planet. Measurements from spacecraft have shown that Venus's atmosphere is not still even where sunlight is weaker. Probes and orbiters detect winds, temperature structures, cloud layers, and chemical patterns. These observations support a picture of a dense atmosphere with strong vertical and horizontal coupling. Coupling means that one part of a system can affect another through physical exchange. In Venus's middle atmosphere, coupling occurs through moving air, radiation, waves, and pressure. The region does not behave independently. It helps connect the bright upper clouds to the deeper atmosphere and indirectly to the solid planet. As the inward path moves through this middle region, Venus becomes less like a shining point and more like a layered engine of air. The cloud cover is no longer only a reflective screen. It is part of a moving, heated, chemically active atmosphere with enough mass to matter in the planet's rotation. The slow backward spin remains hidden below, but the conditions that may help maintain it become clearer. The middle atmosphere carries sunlight into motion, motion into pressure, and pressure into long exchanges with the planet. In this region, the reason for Venus's strange spin begins to take shape not as a single event, but as the patient work of a heavy atmosphere surrounding a slowly turning world. Beneath the middle atmosphere, Venus enters its lower air, where the weight above grows into one of the defining conditions of the planet. This region lies below the main cloud decks and closer to the ground, though the surface itself remains outside the present layer. The air here is mostly carbon dioxide, compressed by the mass of the atmosphere overhead. Pressure increases steadily downward, and temperature rises with it. The lower atmosphere is not a thin space between clouds and land. It is a deep, heavy medium that presses inward, stores heat, and links the moving atmosphere to the hidden solid world. The pressure near the bottom of Venus's atmosphere is far greater than the pressure at Earth's sea level. It is often compared to the pressure found deep under Earth's oceans, where water bears down from above. On Venus, the pressing material is not water but air, made dense by gravity and by the enormous amount of gas surrounding the planet. This pressure changes the meaning of atmosphere. On Earth, air feels nearly weightless in ordinary life. On Venus, the lower air behaves more like a thick fluid surrounding the rocks. It still flows as a gas, but it has a density and force that make it mechanically important. Heat is equally central in this region. Venus's lower atmosphere is extremely hot because the planet's carbon dioxide atmosphere traps infrared radiation, and because the dense air carries and stores energy efficiently. The surface temperature is high enough to melt some metals, though the air itself remains a gas under Venusian conditions. The heat is not simply a daytime effect. The thick atmosphere moves energy around the planet and reduces the contrast between day and night. Since the planet rotates slowly, sunlight reaches different regions over long periods, but the deep air smooths that pattern. The lower atmosphere becomes a reservoir of heat rather than a place of sharp daily cooling. The slow rotation of Venus changes how this lower air behaves. On a rapidly rotating planet, moving air is strongly shaped by the turning of the world beneath it. On Venus, the solid planet turns so slowly that pressure gradients, vertical mixing, and the broad circulation of the atmosphere become especially important. A pressure gradient is a change in pressure over distance, and air moves in response to such differences. In the lower atmosphere, these motions are slower than the upper cloud winds, but they still matter because the air is dense. A slow movement of dense air can carry significant momentum. Nearer the ground, friction becomes more important. Friction is the resistance that occurs when moving materials rub or drag against one another. In an atmosphere, friction acts between layers of air and between the air and the surface, even before the surface itself is described. The lower atmosphere must be understood as the region where this contact begins to matter. Winds passing over the ground can exchange momentum with rocks, slopes, and plains. The effect is small at any one moment, but Venus is a planet of long timescales. Repeated exchanges can influence the balance between atmosphere and solid body. The lower atmosphere also participates in thermal tides. Sunlight heats the upper and middle atmosphere, and the resulting shifts in pressure can extend downward. In a thick atmosphere, these tides are not limited to the cloud tops. They involve a redistribution of mass across layers. When air warms, expands, cools, and compresses in a regular pattern, it can create pressure forces that act on the planet. These forces do not need to be large to matter over geological time. The lower atmosphere, because it is dense, helps make the total atmospheric tide more massive and more capable of exerting a twisting influence. The word tide often brings to mind oceans, but on Venus the atmosphere itself can be the moving tidal body. The sun pulls gravitationally on the planet and also heats its air. The gravitational tide stretches the solid body slightly, while the thermal tide shifts the atmosphere through heating. These two kinds of tides can act in different ways. The solid tide raised by the sun tends to slow rotation and can drive a planet toward a state linked to its orbit. The atmospheric tide can oppose or alter that trend. In the lower atmosphere, the dense air gives the thermal tide much of its strength. This balance is one reason Venus is scientifically important. Its backward rotation is not explained only by saying that the sun slows the planet. A close planet with no atmosphere might be expected to move toward a different kind of spin state under tides. Venus has a massive atmosphere, and that atmosphere responds strongly to solar heating. The lower air is part of the mass that responds. It helps create pressure patterns capable of pushing on the solid planet. The resulting exchange may help maintain a slow retrograde rotation rather than a simple locked condition. Observations and models indicate that atmospheric tides are a major part of the explanation, though the exact path through time remains uncertain. The lower atmosphere is also chemically stable in its broad composition, dominated by carbon dioxide with nitrogen and smaller amounts of other gases. Water vapor is scarce compared with Earth. This dryness matters because it affects clouds, heat transport, and the long climate history of the planet. Yet within this section, the main feature is not the origin of the air but its present physical weight. Dense carbon dioxide presses downward, absorbs heat, and moves in contact with the lower atmospheric layers. It forms a heavy blanket that is active, not passive. In this region, the hidden spin of Venus becomes less abstract. A planet's rotation is not only a motion seen from space. It is felt by every layer that moves, presses, and exchanges momentum around the globe. The lower atmosphere is close enough to the ground to transmit forces and massive enough to store motion. It is warmed from above and below, shaped by pressure, and tied to the larger circulation. The backward spin still belongs to the solid planet beneath, but the lower air stands immediately above that solid world as a dense intermediary. It presses inward on Venus, and through pressure, friction, heat, and tides, it becomes one of the quiet agents in the planet's strange rotational balance. Beneath the heavy lower atmosphere, Venus reaches the solid surface, a hidden world of rock that cannot be seen directly in visible light from space. The clouds and dense air conceal it, but radar observations reveal broad plains, highlands, ridges, fractures, craters, and volcanic forms. This surface is the body whose rotation defines the strange backward spin. The atmosphere moves above it, and sunlight acts from outside it, but the planet's rotation belongs to this rocky globe. In this region, the inward path reaches the ground that turns slowly beneath the bright and moving air. The surface of Venus is dominated by volcanic terrain. Much of it consists of wide plains formed by lava flows in the planet's past. Lava is molten rock that reaches the surface and then cools into solid stone. On Venus, radar maps show that these plains extend across large parts of the globe. They are not oceans, and they are not covered by liquid water. They are dry, hot landscapes shaped by volcanic activity and deformation of the crust. The crust is the outer solid shell of a rocky planet. It records forces from below and impacts from above. Though on Venus, the thick atmosphere changes the way small incoming objects reach the ground. The surface does not show the same pattern of moving plates seen on Earth. Earth has plate tectonics, a process in which large pieces of crust move, collide, sink, and separate over geological time. Venus does not show clear evidence for Earth-like plate tectonics operating today. Instead, it appears to have a different style of crustal deformation. Broad regions are stretched, compressed, cracked, and uplifted. Some areas form highlands that rise above the surrounding plains. Other areas show networks of ridges and fractures. These features show that the solid planet has been active, but not in the same way as Earth. The absence of liquid water at the surface is an important part of this setting. Water weakens rocks, affects melting, and helps plate tectonics operate on Earth. Venus's surface is extremely dry and extremely hot. The high temperature changes the strength of rocks and the way they respond to stress. The dense atmosphere also keeps the surface environment stable in a harsh way, with little ordinary weathering by rain, rivers, or seas. There is no flowing surface water to cut valleys or carry sediment in the familiar Earth-like manner. The land is shaped mainly by volcanic resurfacing, tectonic strain, impacts, and chemical reactions under hot, dense air. Radar images show impact craters scattered across Venus, but not in numbers as high as on very old surfaces such as parts of the Moon or Mercury. An impact crater is a circular depression made when a space object strikes a surface. The number and condition of craters helps scientists estimate relative surface age. Venus's crater record suggests that much of the surface is geologically young compared with the oldest surfaces in the solar system, though exact timing remains uncertain. This does not reveal the original spin of Venus, but it shows that the visible ground is not a simple preserved record from the beginning of the planet. The surface has been renewed and altered over time. The highlands of Venus rise like continents in shape but not in origin. They are not continents in the Earth sense, because they do not float on a system of moving plates with ocean basins between them. They are elevated regions of thickened, deformed crust. Radar mapping identifies large highland areas with complex ridges and folded terrain. Some of these terrains are called tesserae, a term used for highly deformed regions with intersecting ridges and grooves. Tesserae are among the most complex surfaces on Venus. They suggest long histories of stress and deformation in the crust. The volcanic forms on Venus include broad shield volcanoes, smaller domes, lava channels, and circular or oval structures linked to rising hot material from below. A shield volcano is a wide, gently sloping volcano built by flowing lava. The planet also has coronae, which are ring-like features thought to be associated with hot upwellings from the mantle. The mantle is the thick, rocky layer beneath the crust. These features show that the surface has interacted with interior heat. The solid ground is not only a passive shell, it is the outer expression of a warm, rocky planet. This matters for rotation because the solid surface is part of a body with internal structure. The crust, mantle, and deeper regions all share the planet's spin, though they may interact in complex ways. At the surface, the result is seen as one slow, retrograde turn. The ground takes about 243 Earth days to rotate once relative to the distant stars. This motion is not visible to ordinary eyes beneath the clouds, but radar maps allow fixed surface features to be compared over time. Mountains, plains, and volcanic structures become reference points for measuring the planet's turn. The surface also exchanges momentum with the atmosphere above it. Dense lower air rests against the rocks, and winds drag across plains and slopes, Because the atmosphere is thick, this contact is more significant than it would be for a thin atmosphere. The ground can slow air near the surface, and the air can exert stress on the ground. The exchange is tiny compared with the mass of the planet, but over long times it belongs to the total balance of rotational forces. Venus's surface is therefore not isolated from the atmosphere. It is the boundary where air and rock meet. In the present surface region, however, the main scientific focus is the solid world itself. The backward spin belongs to a rocky planet with volcanic plains, deformed highlands, and a hot, dry crust. The ground is concealed by clouds but not absent from understanding. It is mapped by radar, measured by spacecraft, and interpreted through geology. It carries no simple visible marks from Earth, but it holds the landmarks needed to define rotation. Each ridge, crater, and lava plain is fixed to the planet's body. Their slow movement under the stars reveals the direction and rate of Venus's spin. The surface of Venus gives the strange rotation a physical anchor. Above it, clouds move quickly and air presses heavily. Around it, the planet follows a nearly circular orbit. At the ground, the hidden globe itself turns backward with great slowness. The plains and highlands do not explain the reversal by their shapes alone, but they show the nature of the world that has been reversed or slowed into its present state. It is not a lightweight shell or a cloud feature. It is a rocky planet nearly the size of Earth, wrapped in dense air, carrying a surface shaped by volcanism and stress, and turning in a direction that remains one of the most unusual motions among the inner planets. The hidden surface of Venus becomes measurable when observation moves from visible light to radar. The bright clouds block ordinary sight, but radio waves can pass through much of the atmosphere, reach the ground, and return with information about distance, roughness, and motion. This method changes Venus from a shining cloud-covered disk into a mapped rocky world. It also makes the planet's slow backward spin known with precision. In this region of measurement, the strange rotation is no longer only an inference from theory. It becomes a property read from the movement of fixed surface features. Radar works by sending radio waves toward a target and timing the returning echo. Since radio waves travel at a known speed, the delay between sending and receiving gives distance. The strength and shape of the returning signal give information about the surface. Smooth areas, rough areas, slopes, and highlands reflect radar differently. When the same regions are observed repeatedly, their positions can be compared. On Venus, this allows scientists to follow the solid body beneath the clouds. The method is especially powerful because it does not require sunlight or a clear atmosphere in visible wavelengths. Early radar observations from Earth show that Venus rotates very slowly and in a retrograde direction. Ground-based radar can send signals across interplanetary space, strike the planet, and receive faint echoes. These echoes are affected by the rotation of Venus. One side of the planet moves slightly toward Earth while the other side moves slightly away, creating tiny changes in the frequency of the returning signal. This effect is called Doppler shift, a change in wave frequency caused by relative motion. By studying these shifts, scientists measure how fast and in what direction the solid planet turns. Spacecraft later improved this knowledge by mapping the surface in detail. Orbiters carrying radar instruments pass around Venus and build global images from many observations. The Magellan mission, operated by NASA, provides one of the most detailed radar maps of the planet. Its measurements reveal plains, volcanoes, highlands, craters, and ridged terrains. These features are fixed to the solid surface, so they become markers for rotation. As radar views accumulate, the orientation of the planet can be defined more accurately. The hidden world gains a coordinate system, and its turning becomes measurable. The measured rotation period of Venus is about 243 Earth days relative to the stars. This is the sidereal rotation period. The direction is retrograde, meaning that the planet spins opposite the prograde direction followed by most planets. If the north side of the solar system is used as a reference, most planets rotate counterclockwise, while Venus rotates clockwise. The exact wording depends on the chosen viewpoint, but the physical fact is consistent. Venus turns backward compared with the main direction of planetary spins in the solar system. Measurement also shows that the rotation of Venus is extremely slow. Earth completes one sidereal rotation in about 24 hours. Mars does so in a little more than 24 hours. Venus takes longer than its orbital year. This slow movement makes each measurement demanding because the change in surface position is gradual. Radar does not watch a continent slide rapidly across view. It detects a patient turn, one that unfolds over many Earth months. The same slowness that makes the spin unusual also makes it a careful observational problem. The rotation rate of Venus may not be perfectly constant at every measured epoch. Some studies suggest small variations in the length of the Venusian day, possibly related to exchanges between the solid planet and its dense atmosphere. These variations are difficult to measure and remain an area of study. The broad fact is secure: Venus rotates slowly and backward. The smaller details of short-term changes require precise comparison between measurements made at different times and with different methods. This uncertainty does not weaken the main result. It adds a finer layer to the idea that Venus's atmosphere and solid body are linked. Radar mapping also defines the orientation of Venus's axis. The planet's axial tilt can be described in more than one way because of its retrograde spin. In practical terms, Venus is often said to have an axial tilt of about 177 degrees relative to its orbit, meaning that its spin axis is nearly upside down compared with the usual prograde orientation. Another way of describing the same geometry is that the planet is only slightly tilted from being upright, but rotating in the opposite direction. The large number reflects the retrograde convention. The important physical point is that the spin direction is reversed, not that Venus has Earth-like seasons. Because the surface is hidden, radar landmarks become the equivalent of continents and mountains seen from space. A crater, a ridge, or a volcanic plain can hold its position on the globe, while the globe turns beneath the stars. By comparing these features with time standards and spacecraft positions, scientists build a model of Venus's rotation. This model is essential for navigation, mapping, and interpreting geology. It allows each surface feature to be placed in latitude and longitude. Even though no visible surface map exists through the clouds, the measurement of backward spin also separates surface rotation from atmospheric motion. The upper clouds circle the planet in only a few Earth days, while radar shows that the ground rotates far more slowly. Without radar, the atmosphere could be mistaken for the main visible motion. With radar, the moving cloud shell and the turning rocky body become distinct. This distinction is central to understanding Venus. The planet is not a single visible object rotating as it appears. It is a layered system, and each layer has its own motion. In this region of measurement, Venus becomes less mysterious in one sense and more interesting in another. The backward spin is no longer hidden, but its cause remains open to explanation. Radar reveals the fact that must be explained. It does not by itself say whether the present rotation comes mainly from ancient impacts, solar tides, atmospheric tides, internal coupling, or a combination of these processes. It supplies the stable reference point from which those explanations begin. The strange reason for Venus's spin depends first on knowing what the spin actually is. The inward path has now reached the act of revealing. The bright clouds hide the surface, the dense air surrounds it, and radar passes through to measure the ground. Fixed features show a rocky planet turning slowly in a retrograde direction. The measurement is quiet and exact, built from echoes rather than sight. It shows that Venus's backward spin is not an illusion of clouds, not a guess from brightness, and not a symbolic contrast with Earth. It is the actual motion of the solid planet, discovered by listening to radio waves returned from a world concealed beneath light. The backward spin of Venus is described by the word retrograde, which means that a body rotates opposite the main direction of motion in its system. In the solar system, most planets orbit the Sun in the same direction, and most also rotate in that same broad prograde direction. Prograde means aligned with the common direction. Venus travels around the Sun in the prograde direction, but its solid body rotates in the opposite direction. This makes the planet unusual not because it moves backward through space, but because its own turning runs against the general pattern inherited from the early solar system. The meaning becomes clearer when orbit and spin are kept separate. Venus completes its orbit around the Sun in about 225 Earth days. That orbital motion is ordinary for an inner planet. Its rotation relative to the stars takes about 243 Earth days, and the direction is retrograde. The two motions combine to produce a solar day, which is the time from one noon to the next on the planet. On Venus, the solar day is about 117 Earth days. This number is shorter than the sidereal rotation period because the backward spin and orbital motion combine in an unusual way. The terms are technical, but the basic idea is plain. One measure follows the stars, and the other follows the Sun. On Earth, the difference between a sidereal day and a solar day is small because Earth rotates quickly compared with its year. On Venus, the difference is large because the planet rotates slowly and backward. The Sun's apparent motion in the sky would therefore be unlike the familiar motion seen from Earth, although the permanent cloud cover hides any direct view from the ground. The surface does not receive a clear sunrise and sunset in the ordinary visual sense. Light is scattered through the cloud layers, and the atmosphere spreads heat around the globe. Still, the geometry of rotation remains real. The planet's body turns one way while its path around the Sun carries it another way. Retrograde rotation can also be described through the direction of the spin axis. A planet's axis is an imagined line running through its center and poles. For a prograde planet with little tilt, the north pole points toward the same general side of the orbital plane as the north poles of most planets. For Venus, the axis can be treated as almost upside down compared with that usual orientation. This is why its axial tilt is often given as about 177 degrees. That description does not mean Venus has a strong seasonal tilt like a planet leaning far sideways in the everyday sense. It is a way of expressing that the spin direction is reversed. The backward direction matters because planets are expected to begin with prograde spin. In the early solar system, material gathers in a rotating disk around the young Sun. Small particles collide and stick, then grow into larger bodies. As these bodies accrete, meaning they build up by gathering material, they inherit motion from the disk and from impacts. The final spin of a planet depends on many collisions and exchanges of angular momentum. Angular momentum is rotational motion that tends to be conserved unless an outside torque acts. Because the whole disk has a shared direction, prograde motion is common. A retrograde spin therefore suggests that later processes altered the original state or that the final assembly involved unusual events. Venus is not the only planet with an unusual rotation. Uranus rotates with its axis lying nearly in the plane of its orbit, giving it an extreme tilt. Mercury rotates slowly in a resonance with its orbit, meaning its spin and orbital period are linked in a stable ratio. These examples show that planetary spins can be reshaped by collisions and tides. Venus, however, combines slow rotation with retrograde direction and a massive atmosphere. This combination makes it a special case among the rocky planets. Its backward spin is not only a sign of possible ancient disturbance, it is also part of an ongoing balance involving the Sun and the atmosphere. The term backward can sound simple, but the physical meaning is not a moral or directional error. It is a comparison with a chosen reference frame. From one side of the solar system, most planets turn counterclockwise, while Venus turns clockwise. From the opposite side, the visual description reverses, but the relationship remains the same. Venus rotates opposite the common planetary direction. Scientific language uses retrograde to avoid confusion and to keep the comparison precise. The planet is not misbehaving. It is following a rotational state produced by its own history and environment. This definition also helps separate appearance from reality. The upper clouds of Venus move rapidly in the retrograde sense around the planet, completing circuits in only a few Earth days. The solid surface, measured by radar, rotates far more slowly. Both motions may share a direction, but they are not the same motion. The atmosphere's fast superrotation and the planet's slow retrograde spin belong to different layers of the same world. The word retrograde describes the surface rotation of the planet as a whole. It does not reduce all atmospheric circulation to a simple copy of the ground. The slow rate deepens the significance of the direction. If Venus rotated backward very quickly, the mystery might lean more strongly toward a large sudden disturbance. If it rotated slowly in the normal direction, solar tides alone might be easier to imagine as the dominant explanation. Its actual state is both slow and backward. This points toward a history in which more than one influence may matter. The present rotation may reflect ancient formation events, long tidal breaking by the Sun, and persistent atmospheric torques. The meaning of retrograde rotation is therefore not only descriptive, it defines the target that any explanation must reach. A planet's spin affects many other physical processes, but on Venus those effects are filtered through the dense atmosphere. Rotation influences wind patterns, the distribution of sunlight over time, and the way moving air is deflected. Yet the atmosphere is so thick and mobile that it also influences the rotation in return. This two-way relationship is not common in ordinary experience, where air seems too light to affect the ground beneath it. On Venus, the air is massive enough for the relationship to matter. Retrograde rotation is both a property of the rocky body and part of a broader planetary balance. In this region of meaning, the strange spin is given its exact shape. Venus is not simply slow, it is not simply tilted, it is not moving backward in its orbit. It is a planet that travels normally around the Sun while its solid surface turns in the reverse direction, taking longer than its year to complete one rotation against the stars. The word retrograde holds this whole pattern in one term. It marks the difference between Venus and the common rhythm of the solar system. And it prepares the explanation by defining precisely what has to be explained. Long before the present atmosphere settles into its deep and heavy form, and long before the surface becomes a field of volcanic plains, Venus begins as a growing body within the young solar system. This early stage is defined by accretion, the process through which small particles of dust and rock collide and stick together, forming larger and larger bodies. The region near the Sun contains abundant material, moving within a rotating disk of gas and dust. Within this disk, countless collisions occur. Each collision carries motion, and each addition of mass changes the growing planet's rotation. At the start, no single direction is guaranteed for a planet's spin. The disk as a whole rotates in a common direction, but the assembly of a planet is not a smooth and perfectly ordered process. It involves impacts from many angles with different speeds and sizes. Each incoming body brings its own angular momentum, which is the measure of rotational motion. When a growing planet absorbs these impacts, its spin changes. Some collisions speed up rotation, others tilt the axis. Some may slow or even reverse the direction of spin, depending on the angle and force of impact. In this early region, Venus is not yet the calm sphere hidden beneath clouds. It is a forming body, heated by impacts and by the energy of its own contraction under gravity. Large impacts release enormous energy, melting parts of the surface and perhaps creating global magma oceans, which are layers of molten rock covering much of the planet. In such a state, the outer layers are fluid rather than solid. Fluid layers can redistribute mass more easily than solid rock, which means that the planet's rotation can evolve as material shifts and settles. The presence of a magma ocean affects rotation because fluid motion allows the planet to adjust its shape and internal distribution of mass. A spinning body tends to become slightly flattened at the poles and wider at the equator. This shape depends on the rate of rotation. If rotation changes, the shape adjusts. In a fluid or partially molten state, this adjustment can happen more readily. The early Venus, still forming and cooling, is therefore capable of responding to changes in angular momentum through both impact and internal flow. The environment of the early solar system also includes interactions with nearby forming bodies. Protoplanets, which are growing planetary embryos, move within the disk and can influence each other through gravity. Close encounters may alter paths and spins. Some bodies may collide directly, while others pass close enough to exchange energy without contact. These interactions can add complexity to the final rotation state of a planet. Venus, forming near Earth, likely experiences a similar population of neighboring bodies, all competing for material and space. One important idea in this stage is that the initial spin of a planet is not fixed at birth. It is the result of many contributions. The disk provides a general direction, but the details are shaped by stochastic events, which means events that occur in a way that is partly random within the overall system. A single large impact late in formation can outweigh many smaller earlier contributions. This makes the final rotation sensitive to the history of collisions. Observations of the solar system support this view, as different planets show different spin rates and axis orientations. For Venus, the early formation stage sets the baseline from which later processes act. If the planet begins with a prograde rotation, similar to Earth, then later influences must slow and possibly reverse it. If instead a major collision or sequence of collisions produces a retrograde or near zero spin early on, then later forces may act to stabilize or modify that state. The exact initial condition is not directly observed. It is inferred from models of planetary formation and from comparison with other planets. During this early time, the Sun itself is still evolving. Its radiation and solar wind interact with the surrounding disk, gradually clearing gas and dust. As the disk dissipates, the environment changes. The growing planets transition from forming bodies within a dense disk to more isolated worlds orbiting the Sun. The removal of gas reduces drag on planetary motion, and the dominant influences shift toward gravity and internal processes. The timing of this transition matters because it determines how long the planets experience certain forces that can affect rotation. The early Venus may also begin to develop an atmosphere during this stage, either from captured gas or from outgassing, which is the release of gases from the interior through volcanic activity. This early atmosphere is likely very different from the present one. It may contain water vapour, carbon dioxide, and other gases in different proportions. The presence of an atmosphere, even at this stage, introduces the possibility of atmospheric tides and interactions with solar radiation. However, the full development of a dense, long-lived atmosphere occurs later. In this early region, the focus remains on the formation of the solid planet and its initial rotation. Cooling plays a role as well. As the planet radiates heat into space, its surface begins to solidify if it was previously molten. The transition from a magma ocean to a solid crust marks a change in how the planet responds to forces. A solid body resists deformation more strongly than a fluid one. Once the crust forms, changes in rotation become harder to achieve through internal redistribution of mass alone. External torques, such as those from tides or impacts, become more important for altering spin. Observations and models indicate that Earth and Venus likely form under broadly similar conditions, yet their final rotations differ greatly. This contrast suggests that the details of their formation histories diverge in important ways. Earth ends with a relatively fast prograde rotation. Venus ends with a slow retrograde rotation. The difference points to variations in impact history, tidal evolution, atmospheric development, or a combination of these factors. The early formation stage does not provide a single clear answer, but it defines the range of possible starting points. In this region of ancient formation, the strange spin of Venus is approached through accumulation and collision. The planet gathers mass, absorbs impacts, and evolves from a fluid state toward a solid one. Each step contributes to its angular momentum. The final outcome is not predetermined by the disk alone. It is shaped by the sequence and scale of events during growth. The backward rotation observed today may carry the imprint of this early stage, either as a direct result of a major disturbance or as a condition later modified by slower forces acting over billions of years. Within the early history of Venus, one possible source of its unusual spin is a giant impact. A giant impact is a collision between a growing planet and another large body, often a planetary embryo rather than a small meteor. Such an event can change the direction, speed, and tilt of a planet's rotation. It can add angular momentum, remove angular momentum, or redirect it. Because Venus rotates slowly and backward today, large impacts are considered one possible part of the explanation, especially for changing a spin that may once have followed the common prograde direction. A collision of this scale is not a small surface event. It involves a body large enough to affect the whole planet. When such an object strikes at an angle, it can twist the growing world. The effect depends on the mass of the impactor, the speed of the impact, the angle of arrival, and the rotation Venus already has at that time. A direct head-on impact mainly adds heat and mass. A glancing impact can add strong spin or tilt. If the impact arrives from a direction opposite the existing spin, it can slow the planet down. If it carries enough angular momentum, it can even reverse the rotation. The early inner solar system is a place where such collisions are plausible. Planetary embryos move through overlapping paths, and their gravity perturbs one another. Some bodies merge, while others are scattered away or destroyed. Earth's moon is widely understood to have formed after a large impact involving the young Earth, though the exact details remain studied. This example shows that large collisions are not unusual in planetary formation models. Venus, forming in the same inner region, may also have experienced one or more major impacts during its growth. A giant impact explanation has a direct appeal because it can change a planet's spin quickly. Tides and atmospheric effects work gradually, over long spans. A collision can alter rotation in a single event. If early Venus is rotating prograde, a sufficiently strong impact from the right direction could reduce that spin or reverse it. If early Venus is rotating only slowly, a smaller change may be enough to place it near a retrograde state. In this sense, impact history can provide a starting condition for later evolution. The surface of Venus today does not preserve an obvious scar from such an ancient event. This absence is not surprising. The event would have occurred during the early assembly of the planet, when the surface may have been molten or repeatedly resurfaced. Later volcanism, crustal deformation, and thermal evolution would erase or bury ancient impact structures. On a planet with a hot active surface and a long geological history, the lack of a visible basin does not rule out an early giant impact. The evidence must come from models, comparison with other planets, and the present rotational state rather than from a clear surface mark. A large impact also affects more than rotation. It can melt vast regions, change the distribution of materials, strip or add atmosphere, and influence the internal structure of the planet. If Venus receives such an impact, the energy released may help maintain a magma ocean for a time. Heavy elements may sink inward, lighter materials may rise outward, and gases may be released from molten rock. These changes belong to the broader formation of the planet, but the rotational effect remains especially important for the backward spin question. The direction of the impact is central. A planet's spin is a vector, meaning it has both size and direction. An impact carries its own angular momentum as a vector too. When the two combine, the final spin depends on the addition of these directed quantities. A body striking from one side may speed the spin. A body striking from another side may tilt it. A body arriving with angular momentum opposite to the existing rotation may slow it. The outcome is not determined by impact energy alone. It is determined by geometry as well as force. Models of planetary formation allow many possible early spin states for rocky planets. Some simulations produce planets with rapid prograde spins. Others produce slow spins, tilted axes, or retrograde rotations after large collisions. This variety means that Venus's present rotation could begin from a collision-shaped state. However, models also show that later tidal and atmospheric forces are likely important. A giant impact may explain how Venus first becomes slow, tilted, or reversed, but it may not by itself explain why the present spin has the exact slow, retrograde value observed today. This uncertainty is important. Scientific consensus does not identify one confirmed impact as the single cause of Venus's rotation. No direct observation shows the impactor, the time, or the exact collision path. The impact idea remains a plausible mechanism within a larger set of explanations. It is useful because it can account for large early changes in spin, especially changes that gradual processes might find difficult to produce from a fast prograde state. It remains limited because the evidence is indirect and because Venus's later evolution can also reshape rotation. A giant impact may also influence the planet's axis. If Venus is struck in a way that tilts its rotation axis greatly, the resulting motion can be described as retrograde depending on the final orientation. A planet can appear to rotate backward either because its spin is reversed or because its axis is tipped beyond a right angle relative to its orbit. These descriptions are mathematically linked. Venus's axial orientation, often described as about 177 degrees, can be seen as nearly upside down compared with the usual prograde direction. A major impact is one way such a state could begin. The aftermath of a giant impact would not be calm. The planet would radiate heat, melt and reform outer layers, and adjust its shape to the new rotation. Debris might enter orbit for a time or fall back to the surface. Unlike Earth, Venus has no large moon today. This absence does not prove that no giant impact occurred. It only shows that any debris did not remain as a large lasting satellite. Material may have reaccreted, escaped, or been removed by later gravitational interactions. The present lack of a moon adds another constraint, but not a simple answer. In the inward path through causes, the giant impact possibility occupies the region of sudden disturbance. It belongs to the era when Venus is still being assembled and when large bodies still collide. It provides a way for the planet's spin to change sharply, perhaps slowing, tilting, or reversing the young world. It does not stand alone as a complete explanation. Observations indicate the present spin clearly, while the ancient collision history remains uncertain. The impact idea gives one possible opening condition for Venus's backward rotation, a deep early disturbance that later forces may refine into the slow retrograde state seen today. After the era of early impacts, Venus remains close to the Sun, where gravity acts with steady patience. The Sun does not only hold the planet in orbit, it also raises tides in the body of Venus, pulling slightly more strongly on the near side than on the far side. This difference stretches the planet by a very small amount. The stretching is not a visible ocean tide, because Venus has no surface ocean today. It is a tide in solid rock, a slight deformation of the planet itself. Over long spans of time, such tides can affect rotation. A solid tide forms because a planet is not a perfect rigid object. Rock can bend under force, especially when the force acts across millions of years. The Sun's gravity pulls the whole planet inward, but the near side feels a little stronger pull, and the far side feels a little weaker pull. This creates a tidal bulge, a small distortion in the planet's shape. If the planet rotates, the bulge does not always point exactly toward the Sun. Internal friction delays the response. This delay matters because it allows gravity to exert a torque, a twisting influence that changes the spin. For a planet close to its star, tidal effects can be strong enough to slow rotation greatly. Mercury provides an example of a rocky planet whose spin has been shaped by solar tides. Mercury does not keep one face permanently toward the Sun, but its rotation and orbit are locked in a stable pattern. Venus is farther from the Sun than Mercury, yet still close enough for tides to matter. The Sun's repeated pull acts on Venus every moment, slowly removing or redistributing rotational energy through internal friction. Tidal braking is the slowing of rotation by tides. If Venus once rotated faster in the prograde direction, solar tides could gradually reduce that spin. As the planet deforms and relaxes, some rotational energy turns into heat inside the planet. The angular momentum is exchanged with the orbit in a very small way. For a massive planet in a stable orbit, the immediate changes are tiny, but time is immense. Over billions of years, the accumulated effect can be large. The slow present rotation of Venus is consistent with a history in which tidal braking plays an important role. A simple tidal picture might suggest that Venus should eventually keep the same face toward the Sun, rotating once per orbit. This is called synchronous rotation. In such a state, the same hemisphere always faces the star. For an airless close planet, that outcome may be common under strong tides. Venus does not have that state. Its rotation is slower than most planets but not synchronous, and it is retrograde. This difference shows that solid tides alone are not enough to describe the full result. They are part of the inward explanation, but not the whole of it. The near-circular orbit of Venus influences this tidal evolution. When an orbit is highly stretched, the strength of tides changes strongly during each circuit. This can produce complex spin states. Venus's orbit is nearly circular, so the solar tide is steadier. The planet experiences a regular pull, with little variation in distance from the Sun. This steadiness allows long-term tidal effects to act in a smooth way. It also means that other influences, especially those involving the atmosphere, become important in determining why the final state is not simple synchronous rotation. The material properties of Venus affect how tides work. A planet's response depends on the stiffness and viscosity of its interior. Stiffness describes how strongly material resists deformation. Viscosity describes resistance to flow. Hot rock deep inside a planet can deform slowly, even when it remains solid. If the interior is warmer or less rigid, the tidal bulge can be larger or delayed differently. This changes the strength of tidal braking. Since the exact interior state of Venus is not fully known, models of its tidal evolution contain uncertainty. Observations indicate the present rotation, while the detailed internal response remains partly inferred. The dense atmosphere also changes the tidal story. But from the viewpoint of solar gravity acting on the solid planet, the main effect remains braking. The Sun tends to pull the spin toward a lower energy relationship with the orbit. The solid body is stretched and relaxed again and again. Each cycle removes some rotational energy. If the planet begins with a faster rotation, this process slows it. If it begins near a slow state after impacts, the same process can guide it toward a more stable balance. Solar tides are therefore a patient force, not a sudden event. This patience is important for Venus because the planet's present spin is extremely slow. A giant impact can alter rotation quickly, but it does not naturally tune a planet to a long-lasting slow state by itself. Tides can provide that tuning over time. They act continuously, with strength set by distance from the Sun and by the planet's internal response. They do not require visible surface change. They leave no single scar. Their evidence lies in the relationship between orbit, rotation, and physical modeling. In the case of Venus, this relationship indicates that tidal evolution must be considered. The direction of rotation adds another layer. Solid tides tend to reduce the difference between the planet's spin and its orbital motion. Starting from a fast prograde spin, tides slow the rotation towards synchronous behavior. To pass from prograde into retrograde rotation, other effects or initial conditions may be needed. If the spin is already altered by impacts or by atmospheric torques, solid tides can still shape the final state. The present backward spin is therefore not explained by solar tides in isolation. Instead, solar tides define one side of a balance, a steady braking influence acting on the rocky planet. The surface and interior of Venus respond together to this solar pull. The crust and mantle deform slightly, storing and releasing energy. The deformation is tiny compared with the size of the planet, but it is global. The whole rocky body participates. The slow turn of Venus means that tidal bulges and internal relaxation occur under unusual timing compared with rapidly rotating planets. This timing influences the torque. The planet is not simply being held still. It is being continually adjusted by the difference between its spin and its orbital motion. In this region of explanation, the Sun becomes more than the center of orbit and the source of light. It becomes a long-term sculptor of rotation. Its gravity reaches into the solid body of Venus, raising tides in rock and drawing energy from spin through friction. The effect is quiet, steady, and deep. It does not by itself solve the backward direction, but it helps explain the slowness and creates the conditions in which other torques can hold or shape a retrograde state. Venus's strange rotation is partly the result of this patient solar pull, acting across time on a rocky planet close to its star. Within the thick atmosphere of Venus, sunlight does more than warm the air. It creates tides made from heat. These atmospheric tides are not waves in an ocean, and they are not only the direct gravitational tides raised by the sun. They are broad movements of gas caused when sunlight heats one side of the atmosphere more strongly than another. Warm air expands, pressure changes, and mass shifts across the planet. Because Venus has a massive atmosphere and receives strong sunlight, these shifting patterns become one of the central forces in the story of its backward spin. An atmospheric tide is a regular pressure pattern that moves through air. On Venus, the sun heats the cloud layers in the atmosphere beneath them, creating differences between regions facing the sun and regions turned away from it. The heated air expands and changes the distribution of pressure. This creates bulges of atmospheric mass, not solid bulges in rock, but regions where air is arranged differently around the planet. These bulges can be slightly displaced from the line between Venus and the Sun. When that happens, the Sun's gravity can pull on them in a way that produces torque. This torque can act differently from the torque produced by solid tides in the rocky planet. Solid tides tend to slow rotation toward a state linked to the orbit. Atmospheric thermal tides can push in another direction, depending on how the pressure bulges are positioned and how the atmosphere responds to heating. On Venus, models indicate that thermal atmospheric tides may help maintain the slow retrograde rotation against the braking influence of solid body tides. The thick air does not merely follow the planet, it participates in setting the planet's spin balance. The strength of this effect depends on the mass of the atmosphere. Earth also has atmospheric tides, but Earth's atmosphere is thin compared with Venus's, and Earth rotates much more quickly. On Venus, the air is dense, deep, and strongly heated. The slow rotation gives sunlight time to create broad thermal patterns. The massive carbon dioxide atmosphere gives those patterns weight. A pressure difference spread over a whole planet can create a global torque. Even if the force at any one place is small, this is the scale at which air can tug on stone. The cloud layers are important because they absorb and scatter sunlight. Heating does not occur only at the ground. Much of the solar energy is deposited in the upper and middle atmosphere, where clouds and haze interact with radiation. This means the thermal tide begins high above the surface and travels through the atmospheric column. Waves and pressure patterns carry its influence downward and around the planet. The lower atmosphere, dense and close to the surface, helps connect these patterns to the solid body through pressure and friction. Pressure forces act on mountains, plains, and every surface under the air. If pressure is not distributed perfectly evenly, the atmosphere presses more strongly in some regions than in others. The solid planet feels this uneven loading. Over time, as the pressure pattern moves relative to the ground and relative to the sun, the loading can create a torque. The effect is subtle, but the atmosphere of Venus is massive enough for subtle global effects to matter. The planet's slow rotation gives these forces long intervals in which to act. The phrase air-tugging stone is not a metaphor alone. It describes a real exchange of angular momentum between atmosphere and solid planet. Angular momentum can move from one part of a system to another. When winds change, pressure patterns shift, or waves break. The atmosphere gains or loses angular momentum. Through friction and pressure, the solid planet can gain or lose a corresponding amount. The total must be accounted for within the larger Sun-planet system, in Venus. The atmosphere is large enough that this exchange becomes central to explaining the rotation. The atmospheric tides also interact with the superrotation of the clouds. The upper atmosphere moves around Venus much faster than the ground, and this motion stores angular momentum. Waves generated by heating can move that angular momentum vertically and horizontally. Some waves deposit momentum where they fade or break. Others pass through layers and alter circulation elsewhere. The details are complex and remain an active subject of study, but the broad connection is clear. The atmosphere is a moving reservoir, and its motion is tied to solar heating. The timing of the tide matters. If the atmospheric bulge were aligned exactly with the Sun, the pull would not create the same sustained twisting effect. A torque appears when the bulge is displaced. This displacement depends on how quickly the atmosphere heats and cools, how waves move through it, and how the planet rotates. Venus's slow spin and dense air create conditions where the displacement can produce a torque that favors retrograde rotation. In this way, the strange direction of Venus's spin is linked not only to the presence of air, but to the timing of heating within that air. Scientific models of Venus's rotation often describe a balance between solid body tides and atmospheric thermal tides. The solid tides raised in rock tend to break the spin in one way. The atmospheric tides raised by solar heating can oppose or offset them. When the two effects balance, a slow rotation state can persist. Depending on the model and assumptions, the stable state may be retrograde. This does not require the atmosphere to shove the planet rapidly backward. It requires only a long-term torque that, over time, settles the spin into its present slow reverse motion. Uncertainty remains in the exact pathway. The early atmosphere of Venus may not have been identical to the present atmosphere. Its thickness, composition, and water content may have changed. These changes would alter thermal tides through time. The interior response of the planet also affects solid tides, and the original spin may have been shaped by impacts. Observations indicate that the present atmosphere is massive, and that atmospheric tides are physically capable of playing a major role. The precise sequence that leads from early Venus to the present rotation remains a matter of modelling rather than direct observation. Still, among the proposed influences, atmospheric tides provide one of the strangest and most important reasons for the backward spin. They show that a planet's air can help decide how the planet turns. The atmosphere of Venus is not a thin ornament around a rocky sphere. It is a deep mass of gas heated by the Sun, arranged into pressure patterns, and coupled to the solid world below. It can store motion, shift motion, and return motion to the planet through small torques repeated for immense spans of time. In this inward region, the explanation reaches the active boundary between sunlight and air. The Sun heats the atmosphere unevenly. The atmosphere expands, shifts, and forms tides. The Sun's gravity pulls on those displaced masses of air. The air presses and drags against the rocky planet. Through this chain, heat becomes motion, motion becomes torque, and torque becomes part of rotation. Venus spins backward not because the atmosphere alone turns it like a wheel, but because the thick atmosphere helps establish the slow retrograde balance in which the planet now remains. Beneath the surface and mantle of Venus, the inward path reaches the planet's deeper structure, where the rotation of the outer world connects to material hidden far below. Venus is a rocky planet, so its interior is understood in broad layers, crust at the outside, mantle beneath the crust, and a core at the center. The exact details remain less certain than for Earth, because Venus has not been studied by a global network of surface instruments. Still, its mass, radius, density, gravity field, and comparison with other rocky planets indicate that it has a metal-rich core surrounded by a thick rocky mantle. In this inner region, the strange backward spin is considered through coupling between layers. Coupling means that different parts of a system affect one another through physical contact or force. The crust, mantle, and core are not separate planets. They belong to one body, and they share the overall rotation of Venus. Yet they may not respond to every force in exactly the same way. The mantle can deform slowly under pressure and heat. The core may have a liquid outer part, depending on temperature, pressure, and composition. If liquid metal exists in the core, it can move differently from the solid mantle around it. These motions can exchange angular momentum inside the planet. The mantle is the largest rocky layer by volume. It is solid over short times, but over geological time it can flow slowly. This slow flow is called convection, when warmer material rises and cooler material sinks. Mantle convection carries heat from the deep interior toward the surface. On Venus, evidence of volcanic plains and tectonic deformation indicates that interior heat has reached the outer shell in important ways. The mantle's thermal state also affects how the planet responds to tides. Warmer or softer mantle material can deform more easily, changing the size and timing of the tidal bulge raised by the Sun. This tidal response matters for rotation because the Sun's pull does not act only on the surface. It deforms the whole planet slightly. The amount of deformation depends on the interior's elasticity and viscosity. Elasticity is the ability of material to change shape under force and then recover. Viscosity is resistance to slow flow. A planet with a different internal temperature or structure will convert tidal energy into heat at a different rate. Venus's internal properties therefore influence how strongly solar tides slow or reshape its spin. The backward rotation seen at the surface is linked to how the deep body absorbs and releases tidal energy. The core is especially important because it contains much of the planet's metal. For Earth, the liquid outer core helps generate a global magnetic field through motion of conducting fluid. Venus does not have an Earth-like global magnetic field today. This absence may reflect slow rotation, different core cooling, different internal convection, or several factors together. It does not prove that the core is entirely solid. A liquid or partly liquid core may still exist without producing a strong global magnetic field. The internal state remains uncertain, and this uncertainty affects models of rotational evolution. If the core and mantle are not perfectly locked together at every moment, they can exchange angular momentum through friction, pressure, electromagnetic effects if conducting fluids and fields are present, and gravitational coupling caused by slight departures from perfect spherical shape. In simple terms, the deeper interior can resist or smooth changes imposed on the outer shell. When external torques from the Sun and atmosphere act on Venus, the whole planet must respond. But the response may pass through internal layers over time. This can affect small variations in rotation rate and the long-term path toward the present spin state. The shape of Venus is close to spherical, but no rotating planet is perfectly spherical. Rotation, tides, and internal density differences create slight distortions. These distortions influence how gravity acts on the body. A planet with uneven mass distribution can experience torques that depend on its orientation. For Venus, these effects are much smaller than the main solar and atmospheric tides, but they are part of the detailed rotational picture. The interior controls the distribution of mass, and mass distribution affects the way external forces twist the planet. The slow rotation of Venus also reduces the equatorial bulge that a faster spin would create. Earth is slightly wider at the equator because it rotates quickly enough for centrifugal effects to matter. Centrifugal effect is the outward tendency associated with rotation. Venus rotates so slowly that this effect is weak. Its shape is therefore governed more by gravity, internal structure, and tides than by rapid spin. The smallness of the rotational bulge means that Venus lacks one of the stronger stabilizing features found in faster rotating planets. This may influence how its axis and spin state respond over long times. Interior coupling also matters for possible short-term changes in the length of the day. The dense atmosphere can exchange angular momentum with the solid planet, and the interior can affect how that exchange appears at the surface. On Earth, changes in winds, ocean motion, and core motion cause tiny variations in the length of the day. On Venus, the dense atmosphere may cause larger relative effects, though measurements are difficult. The core and mantle may also contribute to subtle changes. These variations do not erase the main fact of retrograde rotation, but they show that a planet's spin is not always a perfectly fixed number. The interior does not provide a simple independent cause of the backward direction. It is not likely that the core alone makes Venus spin retrograde. Instead, the interior controls how the planet responds to outside torques and how rotational energy is dissipated. Dissipation means the conversion of organized motion into heat through friction or deformation. A planet with high dissipation can lose spin energy faster under tides. A planet with low dissipation responds more weakly. Venus's internal structure therefore sets the strength of the patient forces that act from outside. Because direct measurements of Venus's interior are limited, this region of explanation carries careful uncertainty. Scientists infer the core and mantle from gravity, density, planetary formation models, and comparison with Earth. They do not yet have the same detailed seismic knowledge available for Earth, where earthquake waves reveal internal layers. For Venus, future measurements may refine the size of the core, the state of the mantle, and the way the planet deforms under tides. The present understanding remains broad but useful. The interior is a coupled, heat-bearing structure that shapes the response of the whole planet to solar and atmospheric torques. In this deeper region, Venus's backward spin becomes a motion shared by stone and metal. The surface landmarks measured by radar are only the outside of a much larger rotating body. Beneath them, hot rock flows slowly, the mantle transmits stress, and the core may move in ways still partly unknown. External forces act on the planet, but the interior decides how those forces are absorbed, delayed, and converted into heat. The strange rotation of Venus is therefore not only written in clouds, tides, or ancient impacts, it is also carried through the hidden coupling of the planet's inner layers, where motion within rock and metal helps determine how a whole world turns. At the present balance of forces, Venus turns slowly backward beneath its thick atmosphere and steady sunlight. The planet's rotation is not the result of one visible cause acting alone. It is the outcome of a long history in which early formation, possible large impacts, solar tides, atmospheric tides, and internal response all matter. The solid globe rotates in a retrograde direction. The atmosphere moves around it in fast circulation. The sun pulls on both rock and air. The interior absorbs and delays deformation. Together, these parts form a quiet balance that gives Venus one of the most unusual spin states among the planets. The first part of this balance is the starting condition. Venus must have acquired some early rotation while it formed from colliding material in the young solar system. That first spin is not known directly. It may have been prograde, like the common direction of most planets. It may have been slow, tilted, or altered by late impacts. A large collision could have changed the spin strongly, but no ancient record remains clear enough to confirm one particular event. The present planet therefore does not preserve a simple visible answer from its beginning. It preserves a final state shaped by many influences after formation. The second part is the steady pull of the Sun on the solid body. Venus orbits close enough to the Sun for solid tides to matter. The Sun raises small deformations in the rocky planet, and internal friction turns some rotational energy into heat. This tidal braking tends to slow spin over immense spans of time. If Venus once turned faster, solar tides could have reduced that speed. This process is gradual, not dramatic. It leaves no crater and no single surface mark. Its trace appears in the slow rotation itself and in models of how a close rocky planet responds to gravity. The third part is the atmosphere, which changes the result. Venus does not have a thin, passive layer of air. It has a deep carbon dioxide atmosphere with clouds that absorb sunlight and winds that carry momentum around the globe. Solar heating creates atmospheric tides, shifting pressure and mass through the air. These tides can exert torques on the solid planet. In models of Venus, this atmospheric effect can oppose or modify the torque from solid tides. The dense air can help maintain a slow retrograde state, rather than allowing the planet to settle into a simpler synchronous relation with the Sun. The balance depends on timing. A tide must be displaced from perfect alignment to create a lasting torque. The solid body responds with a delay because rock deforms and relaxes under friction. The atmosphere responds with its own delay because air heats, expands, cools, and moves. These delays determine the direction and size of the torques. Venus's slow rotation, strong sunlight, and massive atmosphere create a special setting in which the atmospheric tide can be powerful. The backward spin is therefore tied to the way heat and gravity are out of step in the planet's air and rock. The interior adds another layer to the balance. The mantle and possible liquid parts of the core influence how the planet deforms under tides and how energy is dissipated. A warmer or softer interior responds differently from a cooler or stiffer one. Since the detailed interior of Venus is not fully measured, this part remains uncertain. The broad role is clear: the planet's inner structure controls how outside forces become internal heat, and how efficiently rotation changes. The surface spin is the visible expression of a response that reaches through the whole body. The present rotation may also vary slightly over time. The atmosphere stores angular momentum, and changes in winds and pressure can exchange tiny amounts of that motion with the solid planet. Measurements suggest that the length of the Venusian day may not be perfectly constant, though the details are difficult to establish. This does not change the main fact of retrograde rotation. It shows that the balance is active. Venus is not a clockwork sphere turning in complete isolation. It is a coupled system of air, rock, sunlight, and gravity. Scientific explanations therefore treat Venus's backward spin as a combined outcome rather than a single solved event. Observations establish the present state with confidence. Radar measurements show the solid surface rotating slowly in a retrograde direction. Atmospheric observations show fast superrotation and strong cloud-level winds. Orbital measurements show Venus moving in a nearly circular path close to the Sun. Physical models show that solid tides and atmospheric tides can compete and balance in ways that make slow retrograde rotation plausible. What remains uncertain is the exact sequence through time and the precise weight of each cause. This careful uncertainty is part of the scientific picture. It is known that Venus spins backward. It is known that the Sun's gravity affects the planet. It is known that the atmosphere is massive enough for thermal tides to matter. It is known that early impacts can alter planetary spins. It remains uncertain whether a particular giant impact began the reversal, whether tides alone could have carried the planet through the necessary states, or how the early atmosphere differed from the present one. The explanation is strongest when these factors are considered together. At the inward end of the path, the reason Venus spins backward is strange because it is not only a story of a planet being struck or slowed, it is a story of balance between forces that act in different layers and at different speeds. A collision can act suddenly. Solar tides act patiently in rock. Atmospheric tides act through heated air. The interior controls the response. The surface records the final motion. The result is a world almost the size of Earth. Moving normally around the Sun while turning the other way beneath a bright cover of clouds, Venus's backward spin becomes a quiet statement about planetary history. A planet is not defined only by where it forms or what it is made of. It is shaped by impacts, tides, atmosphere, heat, and time. The present rotation of Venus carries all of these influences in one slow motion. Beneath the clouds, the rock turns against the common direction of the solar system. Above it, the atmosphere flows rapidly around the globe. Around both, the sun continues to pull and warm. The strange reason is not one isolated cause, but a long balance in which air, stone, gravity, and ancient history hold Venus in its slow backward turn. The motion of Venus settles into a quiet image of a planet shaped by time. Its clouds remain bright above the dark surface, reflecting sunlight into space while hiding the ground below. Beneath them, heavy air presses against volcanic plains and highlands. Deeper still, warm rock and metal carry the same slow rotation through the body of the world. Around it all, the sun continues to hold Venus in its orbit, pulling gently on rock and air, warming the atmosphere, and helping maintain a balance that has lasted across deep time. The backward spin is not a single mark left by one moment. It is a present state made from many layers of history. Early collisions may have changed the first rotation. Solar tides may have slowed the planet with patient force. Atmospheric tides may have pushed back through the weight of heated air. The interior may have shaped how each influence was absorbed. What is known is the calm fact measured by radar Venus turns slowly in a direction opposite to most planets, carrying its surface through a long retrograde day. In that slow turning, Venus remains both familiar and distant. It is near Earth in size, yet different in air, heat, surface, and spin. It shines softly from afar, while its hidden world moves beneath clouds that never open to ordinary sight. Its rotation becomes a reminder that planets are not simple stones in space. They are histories in motion, shaped by gravity, light, pressure, heat, and the quiet passing of billions of years.